In this session, we will discuss point estimation and interval estimation in statistics. Estimation is a fundamental concept in statistics used to infer characteristics of a population based on sample data. It helps statisticians and researchers make informed decisions when complete population data isn't available. There are two main types of estimation methods. 1. Point estimation provides a single best guess of an unknown population parameter. For example, using the sample mean, x bar, to estimate the true population mean, mu. While point estimates are easy to interpret, they do not provide information about the precision or reliability of the estimate. 2. Interval estimation, on the other hand, gives a range within which the population parameter is likely to fall, along with a confidence level. Confidence intervals, for example, a 95% confidence interval for a mean, express the uncertainty surrounding the estimate and are more informative than point estimates. Both methods are widely used in statistical analysis, hypothesis testing, and decision-making. This figure illustrates confidence interval estimation in statistics using the normal distribution of a sample mean. The key elements from the figure shown here are: 1. Bell curve, gray curve, represents the sampling distribution of the sample mean, assumed normal. 2. Centerline, x bar, the point estimate or sample mean. 3. Shaded central region, 1 minus alpha, the confidence level, for example, 95%, indicating the probability that the true population mean, mu, lies within the confidence interval. 4. Red areas, alpha by 2, the rejection regions in the tails. Together, they represent the total probability alpha, for example, 0.05 for 95% confidence. 5. Lower confidence limit, shown by the equation x bar minus c, alpha by 2, times sigma by the square root of n. 6. Upper confidence limit, shown by the equation x bar plus c, alpha by 2, times sigma by the square root of n. These two bounds form the confidence interval around the sample mean. A point estimator draws inferences about a population by estimating the value of an unknown parameter using a single value or point. A point estimator provides a single best guess for an unknown population parameter based on sample data. For example, the sample mean, x bar, is a point estimate of the population mean, mu. Although point estimates are useful, they have limitations. Increasing the sample size does reduce the uncertainty of an estimate, but this improvement is not visible from the point estimate by itself. To address this, we use interval estimation, which provides a confidence interval, a range around the point estimate that likely contains the true parameter value. Confidence intervals reflect the effect of sample size. Larger samples typically lead to narrower intervals, indicating more precise estimates. Interval estimation is discussed in the next slide. An interval estimator draws inferences about a population by estimating the value of an unknown parameter using an interval. That is, we say, with some percentage certainty, that the population parameter of interest is between some lower and upper bounds. As an example, suppose we want to estimate the mean summer income of a class of business students. For n equals 25 students, x bar is calculated to be $400 per week. An alternative statement is, the mean income is between $380 and $420 per week. This slide shows once again how the lower and upper limits of the estimated interval are calculated. Lower confidence limit, shown by the equation x bar minus c, alpha by 2, times sigma by the square root of n. Upper confidence limit, shown by the equation x bar plus c, alpha by 2, times sigma by the square root of n. Alpha by 2 is z subscript alpha by 2, used because alpha is distributed between the lower and upper tail region. Some commonly used confidence interval levels are shown here. 1 minus alpha gives the acceptable region. Alpha shows the non-acceptable or rejection region. Left and right tails together. 1 minus alpha and alpha are cumulative probability values. Alpha by 2 is used to calculate the upper and lower cumulative probabilities. The corresponding z alpha by 2 values can be obtained from normal distribution tables. For z alpha by 2 equal to 0.025, the z value corresponding to 0.975 is read from the table, which is 1.96, as shown in the next column. This slide shows how the z alpha by 2 values are read from the normal distribution table. To read the value of z alpha by 2 at alpha by 2 equal to 0.025, 2.5%, we need to look up the z value of 1 minus alpha by 2, which is 0.975. The value is 1.9, from the z values on the left, plus 0.06, from the z value on the top, totaling 1.96. Example 1. Car mufflers are constructed by nearly automatic machines. One manufacturer finds that, for any type of car muffler, the time for a person to set up and complete a production run has a normal distribution with a mean of 1.82 hours and a standard deviation of 1.20. What is the probability that the sample mean of the next 40 runs will be from 1.65 to 2.04 hours? The z values are calculated as shown in the figure. The next step is to read the cumulative probability values from the normal tables. The cumulative probability value corresponding to z equals minus 0.896 is approximately 0.1851, and the cumulative probability value corresponding to z equals 1.16 is 0.877. The required value is 0.877 minus 0.1851, 0.6919. Example 2. A computer company samples demand during lead time over 25 time periods. The data is given in the slide. It is known that the standard deviation of demand over lead time is 75 computers. We want to estimate the mean demand over lead time with 95% confidence in order to set inventory levels. To solve this problem, the sample mean needs to be determined. The sample mean is calculated using the formula as given above. The value of the mean x-bar is 370.16. Similarly, the standard deviation, S, is determined by the above equation. The standard deviation determined is 80.78. In this problem, since the mean, mu, is given, the interval estimate can be calculated using the given value of standard deviation, sigma. When the standard deviation, mu, is not given, the sample standard deviation, S, can be used for the interval estimate. When the sample standard deviation, S, is used, we have to use the t-distribution. In the slide, the upper and lower estimates of the mean of the demand for computers are calculated using the normal distribution. X-bar is 370.16, z alpha by 2 equals 1.96 for a 95% confidence interval. The standard deviation of the population, sigma, is 75 and the sample size is 25. Using the equations x-bar plus or minus z alpha by 2 multiplied by sigma by root n equals 25 will give the lower and upper estimates. In this case, the lower estimate is 340.16 and the upper estimate is 399.56. When the population standard deviation, sigma, is not known, the sample standard deviation, S, along with the t-distribution, is used to calculate the interval estimate. Example 3. A treatment plant that sends effluent into the river claims the mean suspended solids is never above 40 mg per liter. Measurements of the suspended solids in river water on Monday mornings yield X equals 46 and S equals 9.4 mg per liter, N equals 20. Based on data collected over a period of many years, it is reasonable to assume that the individual measurements follow a normal distribution. Do the data support or refute the treatment plant's claim? Given, claimed population mu0 equals 40 mg per liter. Sample mean x-bar equals 46 mg per liter. Sample standard deviation S equals 9.4 mg per liter. Sample size N equals 20. Assume normal distribution, so t-test is appropriate. To determine whether the data support or refute the treatment plant's claim, we need to perform a one-sample t-test on the mean. The t-statistic is determined using the formula given above. The value of t is 2.854, approximately. The critical value of t for a 95% confidence interval, alpha equals 0.5, one-tailed, is approximately 1.729. Since the estimated value of t is greater than the critical value, we cannot accept the company's claim.